Today I will be talking about Lab 6, Magnetic Molasses. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil using Faraday's law and model the magnet and tube interaction computationally and comparing it with predictions. We're going to be using an iPhone, bar magnet, a roll of aluminum foil, a meter stick, and glow script to stimulate everything computationally. Our system will be the bar magnet and aluminum foil tube, and the surroundings will be everything else. Our results consisted of a recorded time of 1.22 seconds, and computationally we found 4.376 seconds. For fundamental physics principles, we will be using Faraday's law of induction, which states that a changing magnetic field creates a voltage in a loop that follows this formula. Next, the Biot-Savart law tells us that a steady current creates a magnetic field around it whose strength follows this relationship below. Lorentz force, which is a force experienced by a charged particle moving in an electromagnetic field, and Ohm's law showing that the current through a conductor is directly proportional to the voltage and inversely proportional to the resistance. We will also be using Newton's second law, which states that the net external force on a system equals changing momentum over time, and then third, which is just the action and reaction. For the procedure of this lab, we marked the north pole of the bar using an app and held the tube vertically, positioned the magnet just above the top opening to ensure that the smartphone captures the entire tube video. We recorded a video while dropping the magnet through the tube and observed the magnet's motion inside the tube compared to free fall. We calculated the fall time by noting when the magnet enters and exits the tube and repeated this experiment 5 times and calculated the average. There is an upward magnetic force created by the induced currents in the tube that slows the magnet down, and this phenomenon is exactly what we are trying to observe and stimulate in this experiment. On the left, I have listed the dimensions and properties of the aluminum tube and a bar magnet that I've used in my experiment, and at the bottom I displayed the changing times for the bar magnet to enter and then leave the tube for 5 different trials. Here's a picture on the right of our experiment. Now it's time for the computational model. I went in and listed all my initial conditions, such as the physical constants and the tube and the magnetic properties. Here's more of the initial conditions. In this section of the code, I calculated the magnetic field of the bar magnet and the change in magnetic flux that it produces. Here I declared all the different forces acting on the magnet, which in this case is the magnetic force acting upwards and the gravitational force acting downwards. Adding these two gave the net force, which I then used to update the velocity and position of the bar magnet. Here's more code computing the B field and magnetic force on the magnet, as well as the net force and position. Here is the visualization of the motion of the bar magnet. In the graph, we see that the magnet enters and exits the tube, and that the gravitational force is greater than the opposing magnetic force, and this causes the magnet to accelerate. However, in the middle of the tube, the two forces seem to balance each other out, and this causes the magnet to travel at a constant velocity. We also see that the time in tube is 4.376 seconds, which is larger than our observed time. A couple questions we can consider to interpret the stimulation. First, which color corresponds to the clockwise current and counterclockwise current? According to Lenz's law, the induced current opposes the change in magnetic flux. Red indicates a counterclockwise current and blue indicates a clockwise current as the current flows to oppose either an increasing or decreasing magnetic field. What happens to the dynamics of the system when you flip the magnet around? The magnet would follow as before, but the direction of the current would just be flipped. How does the total time in tube of your real-world system compare to that of your computational system, and what would make the computational system more accurate? The computational model shows a longer time in the tube, and this could be due to the absence of air, resistance, friction, or other real-world factors. Incorporating these factors, along with more accurate initial conditions and environmental variables, would certainly improve the model's accuracy. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? We see that gravitational force is greater than magnetic force when entering and exiting the tube, but equal within. Some assumptions and errors in our experiment. We assume that there is negligible air resistance. We also assume that the bar magnet acts as a magnetic dipole and that the only forces on the system are magnetic and gravitational. Some errors we had in the experiment included not precisely recording time or inaccurately measuring the magnetic dipole moment. We also didn't consider that magnet could hit the sides of the tube, which slows it down, and that again, air resistance was not considered. Going on to our discussion, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Reducing the resistance to nearly zero would increase the induced current, leading to a stronger opposing magnetic field, and this would result in greater resistance to the magnet's motion, causing it to fall even more slowly. What if holes or slots were cut into the tube? How would this affect the ring currents in our model? Cutting holes or slots in the tube would reduce the number of current-carrying rings, which would weaken the opposing magnetic field, and as a result, the magnet would experience less resistance and fall faster. Thank you.